Hi everyone, welcome. We'll wait another minute for folks to join. As usual, it is right now 6 o'clock, so let's give it a minute. But you're in the right place, as you might have guessed based on the screen. Like more are joining us, so we'll just hang in here for another minute. Hope everyone's having a good week. And hopefully you're finding the content this week, both in terms of the homework and the, when you take the quiz, I think you'll find that they're a little more straightforward than week 2 in terms of the format and having primarily multiple choice questions. So hopefully that's a break for some of you. And obviously I would love to give you more hands-on experience using statistics, but until we get the conceptual stuff down, it's hard to do a lot of the hands-on work. So next week, just as a quick preview, you are going to get your second SAS assignment. I'm hoping to have all the materials for next week uploaded tomorrow. I know I don't usually do it until Monday, but I realize it's the last week, and to take some of the pressure off, I'm at least going to have all the assignments up for next week tomorrow, probably the lectures, and then the one thing that will not be uploaded will be the final until Sunday. I'm not going to upload the final until Sunday, but you will have a full week to work on it, so hopefully that's enough. And I will do a review session during week 4 for the final. So there's some incentive to hold off on taking it until the end. And I do recommend that you work through the lecture content and exercises in week 4 before attempting to take the final exam. It will be cumulative. However, it will primarily emphasize the last 2 weeks of the course when we've been talking about bivariate and multivariate analysis. So things from the first week would mostly be things like things that have been carried forward, like mean and confidence interval. It's the key terms from the first week probably wouldn't need to be reviewed other than a few. I will make also a key term review for the final exam as well. So I'll synthesize from the 4 key term sets from the 4 weeks. I'll pick maybe 35, 25 to 35, somewhere in there, key terms. And that'll also be sort of a study guide for you in terms of what topics will be covered. The final exam will be all multiple choice. There will be some interpretation of output, but there will be no calculations where you wouldn't have an answer provided as of choice. So that should make it go smoother, more smoothly as well. All right, well, I think we have a full group. I am recording this session. I do apologize for last week. The little toggle switch for recording apparently wasn't toggled. I thought I had said it. Always a risk with these Zoom sessions, but this one is being recorded, so I will post this afterwards if you want to review. So I'm going to stick with the format from last week, which was to go over key things that you need to prepare for the quiz. And I don't want to just do it for the sake of the quiz. I also want to kind of emphasize some of the key points from the week and kind of make sure that we understand the core concepts, because they are somewhat elusive without practice. And you will find as you move forward in your careers, especially as you read journal articles that actually interest you, it's hard to motivate people to just do statistics because you have to be interested in a research question. You have to be interested in a problem. But as you start to think about areas of interest, not even just research, just things you care about as a public health person, you're going to naturally gravitate towards some articles that have research content. And hopefully some of the terminology and the methodology that they're using will become much clearer and crisper for you. A lot of the numerical proportions of papers and even the interpretation of those figures and tables will be much clearer to you. You'll also hopefully recognize some of the limitations of what they did, but you'll be amazed when you read a paper after taking a biostats course. You're like, oh, I get what that is. Things your brain probably automatically tuned out as being unfamiliar or potentially as just like overly scientific. I do encourage you to maybe do that on your own. Just pick out some random scientific paper, particularly public health or epidemiology, whatever interests you. See how well you understand what's in there. And that's going to be the goal next week with survival analysis. We won't actually get any hands-on practice doing survival analysis. I won't have you run one, but you'll see a lot of survival analysis done in the literature, particularly clinical literature. So I at least wanted to introduce survival analysis next week as sort of your statistical literacy portion of this course, and just know that it is used a lot in health sciences, as is logistic regression. And that's one reason that next week I'm going to focus a little more on logistic regression. Okay, so back to this week. Some core concepts, and I'm going to give you opportunities to interrupt and ask questions here in a moment. And you're also welcome to put them in the chat. But one of the things that you should be thinking about more and more is the difference between independent and dependent variables. When we started off this course, looking at univariate and bivariate analysis, we weren't too particular about specifying our independent and dependent variables, other than maybe with the t-test where we had to put a response variable and then we had some group variable. But even then, we weren't really thinking of them in terms of independent versus dependent variables. But now that we're moving towards multivariate analysis, and particularly in the regression analysis context, it's very, very important that we specify our independent and dependent variables. So this is one thing that you should know for the quiz and one thing you should know in general. So the dependent variable is sometimes called the outcome. It's also sometimes called the response variable. So those are interchangeable. And in the context of both logistic and linear regression, that would be our y, our dependent variable. Okay, so that's, and usually there's just the one. There are exceptions that we rarely use where there's more than one dependent variable. Okay, so that's really what we're interested in. And one reason why logistic regression is such an important technique is that our dependent variable is often a yes/no kind of answer. Did they die? Yes, no. Did they develop the disease that we're studying? Yes, no. And so the dependent variable is often some outcome of interest. And as I mentioned, often some sort of yes, no kind of response, particularly in our field in epidemiology, public health. Independent variables, and this week we're focused on simple linear regression and simple logistic regression, so we only have one independent variable, but as a group, independent variables, what we call predictors. This includes exposures of interest, any confounders, which we talked about a little bit this week. And another term we haven't used yet in this course is a covariate. things co-vary. They go in this, and that's sometimes used synonymously with confounders. But I just wanted to make clear that those terms are somewhat interchangeable. But the more formal way of talking about these things would be the dependent variable and the independent variables, with some of these synonyms, I guess you call them, depending on the study. So I wanted to review that and just to kind of get you in the habit of specifying your independent and dependent variables, because we are starting to move into prediction of specific outcomes. And there's kind of a logical sequencing where it wouldn't make sense to have something as a dependent variable when it follows sequentially from the independent variable, right? So disease outcome is often considered the result of various exposures over the lifespan. So if we're talking about a dependent variable disease, we would assume that the things that we're interested in are things that preceded that and were potential causal factors or promoting factors. Okay, so hopefully that's all clear. Any questions on independent versus dependent? Okay. All right, so moving on. Scatter plots. So we, in the first week, learned all kinds of graphic techniques for frequencies and using histograms and those kinds of plots. And we got this new nifty one called a scatter plot, and you should know what it's used for. It's specifically used for when we have two continuous variables. And just keep in mind, when I say continuous variables, we also mean interval variables. Continuous would mean that there's fractional numbers. A lot of things are measured on an interval scale where we do whole numbers. But for any two numeric variables, we would use the scatter plot. And it's a super useful tool. And it's used in conjunction often with correlation analysis. You can actually see before you calculate your Pearson's R correlation coefficient what the relationship is. And as you saw in the lecture, you can almost guess what the correlation coefficient is going to be based on that scatter plot. So a scatter plot is simply a plotting of each pair of observations on two variables. So each person, think about a row of data, and they have two continuous measures. We just take their measure on one variable, the measure on the other, and plot that on the XY axis. And it's a really useful tool. You do have to keep in mind that as you get more points, sometimes it can look like too many points and you can't really tell what's going on. There are ways around that. If you had, let's say you had 100,000 people in your study, it would tend to be very crowded on your scatter plot. So what you might be able to do in that case would be to take a 10% sample or something like that that would make the number of like a 10% random sample, and that would prevent you from having too many points to look at. But I don't want to confuse that with I was about to lose power, so excuse me 1 second, that's terrible. 1 second. Oh my gosh, that happened so quickly. My battery must be terrible. Okay, so plots of observations, XY, and you've seen examples of that in the other lectures. So another concept I wanted you to be aware of is correlation. And this past week, we had lectures on correlation and interpretation of those. But I just wanted to re-emphasize the fact that positive and negative relationships are equally interesting. A positive relationship simply means that the variables are moving in the same direction. So as one goes up, the other goes up, and as one goes down, the other goes down. They dance together in the same direction. And so that's one type of phenomenon. But you can think of many others where there's a negative relationship, that as your um, value goes up on one variable, the other is coming down, and the reverse is true. And it's really tempting to think of negative as meaning no relationship or is not as strong as, but these are equally interesting phenomena. So if I take more of a therapeutic drug, let's say it's cholesterol, hopefully my cholesterol level is coming down just as my dosing is coming up. And there's plenty of examples where that would be true as well. And so we're equally interested in positive and negative relationships. And so the correlation coefficient, when we look at the number value, we should always be thinking in terms of the absolute value of the correlation coefficient. The sign tells us whether it's positive or negative. So I just want to emphasize that point. Okay. I just said that. They're equally interesting. So an R, which is Pearson's R of 0.75, is just as strong in magnitude as an R of negative 0.75. And so the range of Pearson's R is -1 to +1. -1 is a perfect negative correlation. +1 is a perfect positive correlation. And I gave you some in the lecture some visuals of what those look like. You can see how the points become tighter on the line of best fit when we get a perfect correlation, and it's a little more scattered when you get less and less correlation. And then if there was no correlation, that is when our Pearson's R value would approach 0. And it would look like a big cloud of points on your scatter plot. So hopefully that makes sense. I don't want you to confuse R with p-values. They have nothing to do with each other. R is a statistic that we compute that is, the mathematics of it are actually pretty straightforward. They're the standardized versions of the two variables. And it's actually like running a regression between two standardized versions of the variables. But we're not going to do the math on it. But that's what it represents. And so hopefully that is clear. Okay, before I move on to the next topic, any concerns or questions about correlations, correlation coefficients, what they mean?
I have a question.
Mm-hmm.
Just so I make sure I understand for the negative correlation. On a plot grid, does that mean like both X and Y axis, correct?
Yeah, I can do a quick visual of a negative versus positive correlation. So let me show you, and let's make sure that we understand what we're looking at when I show you these. So I'm going to quickly stop share and okay. Sorry, just gonna take 1 second to get the right screen up here. Hmm. It's not liking this slide set. 1 second. Okay. Okay, I'll just share my screen. How about that? Okay. It wasn't wanting me to share. So here was an example where we had the relationship between weight and height. And quite obviously, as on average, we're talking about human development, as height goes up, weight's going to go up a little bit. But obviously, it doesn't explain everything about weight, but height is one of the factors. And so on this XY axis, so this is the y-axis, this is the x-axis, but in the case of a scatter plot, it doesn't really matter which you choose, it'll portray the same relationship. So what you see here is that as you increase in weight, which you're looking, so 0 is here for both scales, 0 weight is down here where the y and the x-axis meet. And as we go up in weight, height is also tending to go up in value. So positive value will always look like it's going in that direction, okay? A negative, there's another example of positive, positive, these are all positive. A negative, you'd have this downward slope, and you'll notice here on the x-axis, as values are going up towards 140, they're actually coming down on the y-axis. So this furthest point here, which is our maximum x value at about 130, is actually our lowest y value at 80. So that's an inverse relationship and so on.
Okay. Thank you.
Sure. Yeah, and you can see here that the relative strength of the associations are that, so perfect negative is the same as a perfect, well, that's a nearly perfect positive, but okay.
Okay.
All right, let me go back to all right, let's see, where did I go? I disappeared. Okay, we'll go back to review. Okay, so there I am. Give me a second to appear. So we were at scatter plots, correlation. Okay, so any other questions on correlations? Anything not sinking in? Now's a good time to ask. Okay, we're going to switch modes here and talk about effect modification and confounding. This one trips up a lot of people. They sound similar, effect modification and confounding. So I want to make sure that you all are clear of the difference. So effect modification, which we would actually look for first, which I don't think I mentioned that in the lecture. There is some disagreement on that among biostatisticians, but I always, if you're interested in there being effect modification, meaning you're looking for it, you should look for it first, because it doesn't make sense to present some kind of adjusted result if you've got groups that have really big differences in their effects. But one thing that confuses people when we talk about effect modification, we're talking about the effect being different in two groups for some other variables. So let's say we're interested in smoking and cardiovascular disease risk. So our primary relationship of interest is smoking and cardiovascular disease risk. We're entering now into a third variable, let's say sex, where it modifies the relationship such that in one group, maybe there's a really, really strong effect. And in the other group, there's a relatively weak effect of smoking. Okay. And really, you kind of expect that to be true, right? So if I take a drug as an adult, let's say a therapeutic drug, you would expect a different effect in me, an adult, versus a child who took the same dose or the same drug, right? You're going to expect different effects. And so effect modification simply means that given exposure or given some variable that we're interested in. Are the effects different? Which is really interesting. It's not something we just want to like brush under the rug and adjust it away. We want to report that out whenever it happens. A more telling example is, or a more concrete example, was when the SSRI drugs were first introduced. Those are the antidepressants, certain serotonin uptake inhibitor drugs. It turns out that they really weren't indicated for youth because of increased side effects, whereas among adults, they didn't have as many side effects. And so they very different effects, and we want to know about those differences of effects. So effect modification is usually, we could talk about it as terms of an interaction effect, where in the presence of some other variable, another variable behaves somewhat differently. Okay, so a third variable alters the association. It doesn't cause the association to disappear. It just means it's different between the two groups. So we often look for sex gender differences. We could say another example of an interaction effect would be the effect of smoking is worse among adolescents than adults in terms of asthma risk. Okay, so we've got an association between smoking and asthma risk. And young lungs and kids in general are more prone to developing asthma. And so given the same exposure, yes, it's going to increase risk of asthma for both adults and children, but the effect is stronger among kids than adults. So that's an example of effect modification, and we want to report that out. And so that doesn't mean that age confounds the relationship, that once I adjusted for age, the effect of smoking would disappear. It would just be that there's a difference between those two groups, okay? So it's conceptually really important difference, because we don't want to adjust this out. Normally though, we want to plan in advance to look for effect modification, because basically what we're usually doing is doing subgroup analyses. We're saying, okay, well, what about children versus adults? What about men versus women? And to a certain extent, you have to be careful that you're not just like fishing on a fishing expedition, as we call it, statistics, where you just kind of like seeing what sticks and you're looking for that p-value of something being different. So you want to plan in advance for these things, meaning you have enough participants in your study who are in the two groups of interest so that you can get fairly stable estimates of risk in two groups, and then you can actually say something about difference. So effect modification is super interesting, well, often super interesting, and something that we want to tease out from our data and to report those differences. So like if there's a really strong effect in one group and not so much another, it wouldn't make sense just to present an average risk. We'd want to know what those subgroup differences are. So that's effect modification. It's often easiest to detect with, and I use shorthand 2 by 2 tables. It really should be 2 by 2 by 2 tables. So we've got an outcome versus a dependent variable, and then stratified by a third variable. I should change that in the slide. And the reason I say that is that we can calculate odds ratios or risk ratios in 2 different strata. So basically it's like repeating the analysis twice, once for men, one for women, and saying, is the relative risk that we obtain in men about the same as women? Is it the same in older adults as it is kids? So what we observe often is that the effects are different across the strata, and then we say that there's effect modification happening. And if that is happening, the crude estimate, meaning the estimate that we got for the entire population or the whole sample, falls somewhere between the 2 strata. Okay, so if adults are really low risk relative, or the effect of smoking is not as strong in adults, but it's stronger in youth, the average should be somewhere in the middle, and that would not be a case of confounding. Okay. Confounding, I would say bad. We expect a certain amount of confounding, but it's kind of the fact that when we do observational studies in particular, we don't have really, we have to account for lots of different variables. The beauty of randomization is that when you randomize people in a study, all those potential confounders kind of disappear because we assume that randomization will make those things evenly balanced between the two groups. That includes both measurable and unmeasurable things. But a lot of the time we're doing observational studies, cohort studies, case control studies, cross-sectional studies. Most of the studies we do in epidemiology are observational. And so we have to take into account multiple factors, and it's not sufficient to just report out one variable against one outcome. The only case that's true is in a randomized clinical trial. Everything else you need to do adjustment. So confounding is when a third variable that biases the association between a dependent variable and the outcome. Oh, that was written wrong. That should be an independent variable. X that out. Sorry. I will change that slide before I post it. That should be independent variable in the outcome. So it's a third variable that biases the association between the independent variable and the outcome. And so a good example would be any number of lifestyle risk factors are often confounded. So when our disease outcome is cardiovascular disease or Alzheimer's disease or any of these things that have a sort of complex etiology, meaning multiple causes, it's really hard to tease apart the separate differences attributable to all the different things people are exposed to. They tend to cluster together. So for example, maybe we have a measure of physical activity, we have a measure of diet, and we find in crude analysis that both are significant. However, when we put it in a multivariate analysis, that original fact that we saw for physical activity was somewhat attenuated or changed once we include diet in the model. And maybe the effect may not disappear, but it just changes a little bit, or maybe it diminishes, usually it diminishes a little bit. Likewise, something like smoking and alcohol use. Not to say that everyone who smokes drinks and vice versa, but there are a lot of people who engage in one activity, engage in the other. And so if we want to isolate the effect of smoking, let's say, we may have to adjust out the effect of alcohol because they're confounded, meaning they're mixed together. The effects. And so that's when we kind of want to use multivariate analysis to adjust out those effects. Age is often a confounder, partially because age is very often related to outcome in health-related research, cancer risk, you name it. A lot of things increase the risk with age. Not universally true, but most things. And also a lot of exposures, including the opportunity to be exposed, right? So have you ever experienced, radiation or something like that, or any number of exposures? You're just more likely to have had those things as you get older as well. And so there are a lot of situations where if you don't adjust for age, you may have overestimated the effect. Okay, so that's one reason why a reviewer would almost expect you to include age in a multivariate model because they know it's really important. Your failure to adjust for it would be considered a major limitation of the study. Okay, so confounding is something we do all the time. We take care of confounding all the time in multivariate models. We just want to get rid of it because we're interested in the independent effect of whatever we're interested in. Whereas effect modification, that's more of a design question. Like it might even be, let's say we had 3 aims of our study, and maybe one of those aims was to look at differences across subgroups, even like a health disparities kind of question. That would be kind of more like effect modification. But we can look for both of them when we do stratified analysis to see if the effects are different. Okay, and in the case of confounding, when we do that stratified analysis, what we'll notice is that the crude estimate, meaning that which was based on the entire sample, is not a good average of the stratified estimates. In fact, often what will happen, let's say it's a risk, we calculate it as being a risk factor of like relative risk of 4. And we notice that if we stratify it, it's only as high as 2 in each of the strata, but yet our crude rate was 4. That has to do with the fact that that exposure is imbalanced with respect to some other variable that's also predictive of outcome. And so our failure to take into account its association with another exposure kind of overestimates its effects. So this happens a lot, like I said, with lifestyle risk factors, but there's all kinds of things. So that's one way to visualize or do an initial test for confounding. Often we can then use the original units of the variable, let's say it's a continuous measure, and then adjust for it that way. Okay. So in this case, the observed relationship between some factor and outcome decreases usually. That means, so like the relative risk was 2 and now it's 1 or something. It goes down to 1. Well, that would be perfect or complete confounding. But let's say it goes from 4 down to 2 as a relative risk after you adjust. That would be evidence of at least partial confounding. You still have an effect left, relative risk of 2 after adjustment, but it's nowhere near as high as the crude estimate, which is 4. So we adjust to deal with confounding. You often hear about age-adjusted results or age-adjusted whatever, age-adjusted risk. But we also adjust for other, we can adjust for socio-demographic factors, we can adjust for poverty status, any number of things that we think are important confounders. Okay. So the overall message, confounding and effect modification are different things, even though they sound kind of similar. And our ways of assessing them can often be similar, where we're trying to detect them from 2x2 tables. But confounding is a nuisance that we hope to minimize through adjustment. Effect modification is something interesting that we report when subgroups exhibit different patterns of exposure-disease relationship. Okay, so that is the difference between the two. And we can always assess those using 2x2 tables. Any questions about effect modification and confounding? Clear as mud, right? Okay, well, I will make these slides available in addition to this recording, and you can always quiz yourself on these concepts. And it is one of those things that becomes more clear as you gain practice in doing data analysis, and especially as you're motivated to answer your own research questions, these kinds of questions will come to mind. I say, well, hey, I wonder if there's a difference between men and women. That's an interesting question. But the confounding will be like, uh-oh, I forgot to adjust for this. I wonder if my thing that I was all excited about is finding an association will disappear once I adjust for age. So that's kind of what you experience in doing analysis, is that you have your crude estimates before you've adjusted, and as you add variables, you'll see that because of confounding, it might actually disappear. Which you want to have happen if that's what the reality is. It's not like you want there to be some particular effect. Okay, so that's confounding and effect modification. So I wanted to distinguish between those, and you need to know the difference. Linear regression. We are scratching the surface of linear regression this week, and then we'll get into a little more next week. But what I want you to take home this week is that in linear regression modeling, the outcome variable is always a continuous measure or interval level. I use those terms interchangeably. That's just a numeric value, okay? Blood pressure, heart rate, things that are numeric. And so it's not categorical and it's not dichotomous. So that's important to know, and there's no exceptions to that. Linear regression always has a continuous outcome. Our predictors are independent variables. Oh gosh, I have another typo in here. Okay, this will be changed before. Predictors are independent variables. See how easy it is to mess those up? Independent, dependent. I've done twice already. Our independent variables can be continuous, interval, or indicator dummy variables. Okay, so it's kind of, I don't want to say it's a trick, but it sort of is. The fact that we can include yes, no variables in a regression model. Basically, it's because we can treat 0 as not in the group and 1 as being in the group. And so we can model change from being a 0 to being a 1. So for example, if we had a variable called male, where 1 equals male and 0 equals female, we can include an indicator variable or dummy variable to indicate membership in that category. And it's interpretable because it basically is like saying, oh, well, all things in linear regression are 1 unit change. So a 1 unit change in the variable male is going from no to yes, okay? And you can do that kind of coding with any number of categorical variables. So it's super useful that way, and that you can have your dependent variable as continuous, and then you can basically find a way to include any other kind of variable. Because you can always make ordinal measures categorical and so on. So there's usually a way to include it in a linear regression model. And as we get into multivariate linear regression, multiple linear regression, that just simply means when we put multiple independent variables. And it really depends on the discipline and the science of how many variables we include in multiple linear regression. Economists, they'll throw everything into the model. They're like trying to skim off pennies, right, in some model. And so if it can get you like a quarter of a penny, they're into it. Like, then so let's throw everything in the model. But the equivalent in health is not usually the case. We're not really interested in things that predict like a 0.5% change in probability of health outcome. Maybe that'll change once you get into this like genetic information stuff, but we don't necessarily care about every possible explanatory variable. Even though we talk about simple linear regression, rarely will we use simple linear regression, where you just have one dependent variable and one independent variable. We usually do multiple linear regression. But the important thing to know, a couple of things comparing it to correlation. One is that regression coefficients are in the original units of the variables. So if we have an equation and we have a coefficient, that tells you how much our outcome variable y is changing as a function of that particular x variable next to that coefficient. So if we see a beta value of 3.4 and the outcome was heart rate, that means that as that x variable increases by 1 unit, the heart rate will go up by 3.4 units of heart rate. So it's different than correlation, where we're looking at standardized units, and it's useful that way, but it's also kind of have to be careful, because thinking about things that are measured on different scales can be a little tricky. And so though it's a bonus that it's in the original units, it also can be hard to think about what is a 1 day change in lifespan, or what is a 1 pound increase in weight equal. So that's something to keep in mind. Okay, so that's what I want to talk about with linear regression, and again, we're going to hit on linear regression more next week. Logistic regression as well. Logistic regression, the most important thing to know is that the outcome variable is always dichotomous. And the one reason we use logistic regression as much as we do in epidemiology and medicine is that we often talk about disease that way. We often dichotomize things. Yes, no, they have a certain disease. We're predicting some occurrence, some event that happens. Time to remission in cancer, or time to readmission to the emergency department following something else, or some other outcome. It's usually framed as a yes/no event, and so we need models that can do that. And thankfully, logistic regression came to the rescue and allows us to do that. The mathematics of it are much more complicated than linear regression, but it allows us to predict the likelihood of an outcome, specifically the odds of an outcome, using logistic regression. Just like with, oh gosh, this slide's bad too. Just like with linear regression, our predictors can be continuous, interval, indicator, or dummy variables. So the things that we throw in the model can be pretty much anything. We can either indicator code it 0, 1, or throw it in there as age, or we can, we can use any kind of variable. Okay. And so our regression coefficients in logistic regression, we often have to convert to an odds ratio. Thankfully, we can get our stat software to do that for us, so we don't actually have to mechanically calculate the odds ratio. But it's kind of a quirk of logistic regression that the mathematics behind it, what we're actually calculating is the log odds of the event happening, which is not interpretable. So when we get our coefficients to make them meaningful, we convert them to odds ratios, which again is kind of magical that we can do that because otherwise it wouldn't be very useful. All right, so those are the main things for this week. And I realize introducing linear regression and logistic regression in 1 week is pretty ambitious. And so that's why next week we'll get some more practice. But the main thing here is the outcome variables being different. Linear regression has continuous or interval, and logistic regression has dichotomous. Otherwise, how we put variables into those models are very similar as far as the independent variables. And I will correct that on the slide. Okay. So those are my main review things for the quiz. Hopefully that will set you up for success on that. Any questions about any of that? Okay, where are we with time? Okay, we're at 6:50. So I was going to switch gears and talk about homework. One second. I need to reopen that homework. All right. Oops. I don't want that one. That's next week. Okay, here we go. There we go. Gosh, Okay, I had too many screens open. So homework 3. In a study of the effect of smoking on risk of Alzheimer's disease, based on a crude analysis, it showed that alcohol intake was a risk factor for Alzheimer's disease. No joke, I actually worked on the study. My first study out of college was Alzheimer's case control study that was looking at the effects of smoking. But after adjustment for smoking, the relative risk was 1.0, okay? So basically, before adjustment, it said that it was a risk factor. Let's say it was 4.0. Okay, it doesn't matter what it was, but it showed it being a risk factor. But after adjustment for smoking, oh gosh. Oh yeah, right. Okay, so the relative risk for alcohol intake was was a risk factor. After adjustment for smoking, the relative risk associated with alcohol intake went down to 1.0, basically no risk. So what would that be an example of? Might want to talk about that.
Would it be confounding?
Yeah, when we see a risk estimate change from significant to non-significant, or a big effect down to nothing or to very little, that is confounding, yes. I didn't say how much, how big the effect was for alcohol, and that was on purpose, but usually when the risk estimate changes by more than like 10% after adjustment, we say it's a confounder. In this case, it went from being a risk factor, something that we would have reported out, to nothing at all. And so that would also be like a perfect example of confounding. Okay. So thank you for sharing that. And if you're all here and want to jot that down, go for it. In a study of new treatment for cardiovascular disease, women showed an improvement of 20% compared to placebo, while men showed only a 5% improvement over placebo. So what we have here is a randomized clinical trial, and we found a pretty good effect in women, 20%, and 5% in men. And the study found that the combined improvement for men and women was 12.5%, which is kind of somewhere between 5% and 20%. What is this an example of?
Would that be effect modification?
Bingo. Yes, that would. Do you want to explain why? Or to... You don't have to. So yeah, so in this case, right, we would be interested in reporting that out because, you know, yeah, there's an overall effect of 12.5%. That's great, newsworthy, well, or study worthy, reporting out worthy. But it would be silly to say, well, we noticed that the men, we got this 20% difference, and women 5%. So we might want to design another study to examine why there's these sex differences. Maybe we have to figure out like the dosing levels have to change for between men and women, and maybe we can see a better effect in men if we change the dosing or something like that. So this is something we would want to see. Well, I should say it's interesting, and it points to maybe some underlying causal mechanism. In this case, some mechanism that's beneficial that, okay, well, women are having this great response to this drug, men aren't doing as great. If we could figure out why there's this difference, maybe we can have greater improvement in both groups. Okay, so not to beat a dead horse, but that's a totally different scenario than what we saw above, where we said, oh, wow, we saw that alcohol is a risk factor, but if you adjust for smoking, it just disappears. Here we're saying it's just different across the two groups. Awesome. All right, you calculate the correlation coefficient R between total cholesterol and blood pressure and find that the correlation is strong and positive which of the don't shout this one out. Which of the following correlation coefficients would most likely represent that relationship? So the key here is strong and positive. I bet you can all figure that one out. Shout it out.
D.
Which one?
D.
Yes, okay. I thought I heard B and I almost panicked. B, C, and D all the same. Ah, D, yes, thank you. Right, and so a strong positive would be +0.5. What would be a strong negative?
A.
Thank you. Awesome, and equally strong, right? Just opposite direction, okay? So awesome. We are getting correlation coefficients. That's the goal, right? That's always the goal with learning. We just want you to know this stuff. All right. In a study of hypertension patients, you find that the higher the dose of treatment, the lower the systolic blood pressure, -0.50. This would be an example of a.
Is it D?
D?
No association.
I thought it was a moderate negative relationship.
Okay, we got lots of votes. All right, so let's divide it into two parts. The direction and the magnitude. The direction is what? R equals -0.50.
Negative. Negative. Negative.
right?
Yeah.
So we can rule out A because this is positive. What would the correlation coefficient be if there was no association? What would it look like?
I thought it was 0.
0.
Right. Okay. So don't forget, it's symmetrical around 0, where 0 is no relationship. 1 is perfectly positive. -1 is perfectly negative. So we can eliminate C. We're down to B, and now we're into the realm of interpreting the magnitude of the correlation. And in your notes, in your book, in the slides, these are more rules of thumb than anything. So there's no like magic cut point for a strong correlation versus a moderate versus a weak. But generally speaking, we would say strong once we hit around 0.75. Okay, absolute value. So what do we have here?
It's D, right?
Which one?
It's a moderate negative relationship.
Moderate negative relationship. Yes. That, and in fact, it's exactly. Well, I shouldn't say exactly. We had a moderate positive relationship between height and weight. When in that example, the big scatter plot that I showed you, that's what a moderate positive looks like. So yeah, well, like there's an association between height and weight. Of course there is, but like, is it explaining everything? No. And so that's a good example of where, yeah, there's a really strong relation, or sorry, there's a moderately strong relationship, but there's a whole bunch of other things that one would want to know about someone before determining something like weight. And so that's a good example. All right, so awesome. I think we're getting this. This scatter plot below represents a strong negative relationship.
True.
Our
It's
other
A. True.
options fall, so we've got 2 votes. All right, so let's examine this graphically. So we have our x-axis here going from 0 to 140, and oh, actually it says 40. This is not a good graph. It should go from 0. Okay, and this one is going from 0 to 140 here. So as the values move this way on the x-axis, as they go up on the y-axis. Can everyone see that? So our highest value here of 140, let's say on both, is all the way up here to the right. So as y is going up, when y hits its highest value, x is also hitting its highest
Oh, it's B.
value. Yes, okay, thank you. Let's just cut to the chip. Yes, but no, and honestly, it's not instinctive or intuitive, I should say, to look at the correlation and say, oh, it's this. I think the best way to think about it is just look at the values and say, well, what is happening? Look at the x-axis, look at the y-axis and say, are they going up together? Okay. If it was negative, it would be going like this. As x going up, y is coming down. Okay. So yeah, it is easy to get your head spinning on that one. So just look at the actual values, plug them in. Okay. The correlation shown in figure 1 is stronger in magnitude than in figure 2, figure 1 and figure 2. So we've got an R of 0.4. Here's a good example of positive relationship. And then here's negative, and it's R minus 0.4. What do we got here?
I think it's false.
Right. Because.
Same. They're the same. Yeah.
Yeah. Woohoo. All right. So it's really easy because we talked before with like p-values and stuff. Like one, negative value. I'm sorry, low values, high values, things like that. It's easy to confuse these things, but for correlations, the magnitude and the direction are important. All right. Oh, that was it. So hopefully you all took good notes, or you're gonna have to suffer through this whole thing again tomorrow to get the answers. All right, well, we are fresh out of clock time. However, I am more than willing to answer general questions. And they can be things about things upcoming as well. Oh, there's a chat. There's always a chat. Oh, is this just smiley face? All right, well, I think we did it. I think we're getting this. And it looks like for the quiz, definitely watch the lectures. I posted the 2 slide versions, the PowerPoint versions without me talking. And then you have the 2 versions with me talking. And then you've got the key term review. But I also will post the slide deck from this for your review. So you should be all set. And like I said, I am going to post week 4 a little early so you don't have any panic next week and you have plenty of time to finish that up. So you all have a good weekend and I'll talk to you soon.
Thank you. Bye.
Bye.
Thank you. Bye.